Chapter 1. The Relativity We Are Used to. Does every assertion make sense? Obviously not. Even if we take some words and link them together in strict accordance with the rules of grammar, the result may be complete nonsense. There's no sense whatever, for example, in the assertion that water is triangular. However, not all nonsense is so obvious. All too often, an assertion which appears quite reasonable at first glance turns out to be absolute nonsense under closer scrutiny. Right or left? On what side of the street, right or left, is the house? You cannot possibly answer this question offhand. If you go from the bridge towards the wood, it will be on your left-hand side. And if you go in the opposite direction, it will be on your right. Speaking of the left or right-hand side of a street, you must mention the relative direction. It is quite all right to speak of the right bank of a river, because its current determines the direction. We can similarly say that a motor car drives along the right-hand side of the roadway, because the flow of traffic indicates the relative direction. The notions right and left are therefore relative and make sense only when the direction is given to guide us. The answer depends on the location. Is day or night now? When it is day in Moscow, it is night in Vladivostok. There is no paradox here. Simply, day and night are relative notions, and you cannot answer the question without referring to the place. Who is bigger? In the top drawing of the next page, the cowherd is obviously bigger than the cow. In the lower drawing, the cow is bigger than the cowherd. This is no incongruity either. The two pictures were drawn from two different points, one closer to the cow and the other closer to the cowherd. It is not the true dimension of an object that are essential for a drawing, but the angle at which they are viewed. At these angular dimensions of objects are quite and obviously relative. It is senseless to speak about angular dimensions of objects unless the latter are pinpointed in space. For instance, there is no sense in saying that a tower is seen from an angle of 45 degrees, but if you say that a tower 15 meters away from you is seen as an angle of 45 degrees, that is quite reasonable. It follows, moreover, that the tower is 15 meters high. The relative appears absolute. If we shift our point of observation slightly, the angular dimensions will also change slightly. That is why angular measurements are often used in astronomy. Stellar maps are supplied with angular distances between the stars, i.e. the angles at which the distance between the stars is seen from the Earth. Regardless of our movements on Earth, and regardless of our point of observations, we shall always see the stars at the same distance from each other. This is due to the tremendous, inconceivably great distance that separate us from the stars. Compared to them, our movements on Earth from point to point is so insignificant that we may easily disregard it. Therefore, in this case, angular distances may be accepted as absolute distances. If we take the Earth's rotation round the Sun into account, the change of the angular measurement becomes noticeable, although hardly significant. The picture would change radically, however, if we were to shift our observation point to some stars. Sirius, for example. All angular measurements would be different, and we would find the stars which were far apart in our sky closer together and vice versa. The absolute turns out to be relative. We often say up and down. Are these notions absolute or relative? At different times, people gave different answers to this question. When people did not know that our Earth was round and imagined it to be as flat as a pancake, the vertical direction was regarded as an absolute concept. It was assumed that the vertical direction was one and the same at all points of the Earth's surface, and that it was quite natural to speak of the absolute up and the absolute down. When it was discovered that the Earth was round, the notion vertical collapsed. Indeed, Earth being round, the direction of a vertical line depends essentially on the position of the point on the Earth's surface through which that line passes. At different points of the globe, the vertical direction will be different. Since the notions of up and down thus lost sense. Unless the exact point of the Earth's surface was specified, the absolute became relative. There's no one vertical direction of the universe. Therefore, for any direction in space, we may specify the point on the Earth's surface at which the direction will be vertical. Common sense protest. All this appears obvious to us today as we do not doubt it in the least. Nevertheless, we know from history that it has not been easy for human beings to realize the relativity of up and down. People are inclined to ascribe absolute sense to concepts if the relativity is not evident from everyday experience, as in the case of right and left. Let us recall the absurd objection to the fact that the Earth was round, which came down to us from Middle Ages. How, it said, can people walk upside down? The argument is wrong because it overlooks the relativity of the vertical direction that stems from the Earth being round. If we did not recognize the relativity of the vertical direction and took it to be absolute in Moscow, for example, then naturally people in New Zealand would be walking upside down. But bear in mind that for New Zealanders, we Muscovites too are walking upside down. There's no contradiction in that at all, since the vertical direction is not really an absolute concept, but a relative one. We begin to feel the true meaning of the relativity of vertical directions only when we consider 2 points sufficiently far apart on the Earth's surface, Moscow and New Zealand, for example. If, on the other hand, we take 2 points that are close to each other, 2 houses in Moscow, for example, we are justified in considering all verticals in them to be practically parallel, that is, absolute. It is only when we deal with areas comparable in size of the Earth's surface that the attempt to apply an absolute vertical leads to absurdities and contradictions. The examples which we discussed above show that many of the concepts that we use in our everyday lives are relative, and that they make sense only when we specify the conditions of the observation. Chapter 2. Space is relative. One and the same place or not. Often we say that 2 events occurred in one and the same place and tend to ascribe absolute meaning to our assertion. But in reality it means nothing. It is the same as saying it is 5 o'clock now without specifying where, in Moscow or Chicago. To understand this properly, let us imagine that 2 travelers have arranged to meet every day in one and the same compartment aboard the Moscow Vladivostok Express and write letters to their husbands. Their husbands would hardly agree if we told them that their wives met at one and the same point in space. They would say that these points were hundreds of kilometers apart and would be quite right. Did they not get the letters from distant cities, Yaroslav, Perm, Sverdlovsk, Tumen, Omsk, and Krabovsk, successively? These 2 events, writing letters on the first and the second day of the journey, occurred in one and the same place from the point of view of the wives, and in places hundreds of kilometers apart from the point of view of their husbands. Who was right, the wives or the husbands? We have no grounds to side with either of them. It is quite evident to us that the concept at one and the same place in space is relative. Similarly, the assertion that 2 stars in the sky coincide makes sense only if it specifies that they have been observed from the Earth. 2 events may be said to coincide in space only if we mention the bodies in relation to which the events are located. Thus, the concept of position in space is also relative. When we speak of the position of the body in space, we always imply its position relative to other bodies. If we do not mention the bodies in our answer to a question concerning the position of a given body, the question will lack sense. How a body really moves. It follows that the concept of shifting a body in space is also relative. If we say that the body has shifted in space, we mean that it merely changed its position relative to other bodies. If we observe the motion of a body from various points that alter their relative positions, we shall notice that its motion varies. A stone dropped from a flying plane falls in a straight line relative to the plane, but it describes a curve known as a parabola relative to the Earth. How does the stone travel in reality? There is as little sense in that question as there is in the one about the angle at which the moon is seen in reality. If observed from the sun or from the Earth, the geometrical shape of the curve along which a body moves is just as relative as a photograph of a building. Just as we obtain different photographs when we snap a building from the front and from the rear, so too do we get different curves when following a flight of stones from different points. If we limited our interest when observing the motion of a body in space to study the trajectory, the curve along which the body moves, we would be guided in our selection of a place of observation by considerations of convenience and simplicity. A good photographer, when he selects a spot for his camera, is concerned, among other things, with the aesthetic side of his picture, with its composition. But in studying the motion of bodies in space, our interest is broader. Not only do we want to know the trajectory, but also to predict the path of a body in given conditions. In other words, we want to know the laws governing motion, the laws that induce bodies to move one way or another. When we examine the relativity of motion from this point of view, we find that not all positions in space are equivalent. If we ask the photographer to snap us for an identification card, it is our face that we want photographed and not the back of our head, which determines the position in space from which he photographs us. No other position would meet our requirements. The state of rest is found. The motion of bodies is influenced by external forces. A close examination of this influence will provide us with an entirely new approach to the problem of motion. Let us assume that we have a body at our disposal which is not influenced by any external forces. This body will move in a more or less bizarre fashion, depending on the point of our observation. But it is obvious that the most natural position for the observer will be the one in which the body is simply at rest. We can therefore now give a completely new definition of the state of rest, irrespective of the movement of the given body relative to the other bodies. Thus, a body free from the influence of any external force is in a state of rest. Internal frame. How can we bring about a state of rest when we can be sure that a body is not influenced by any extraneous forces? For that purpose, we must take that body as far away as we can from all other bodies that might affect it. We could in our imagination build a laboratory, a frame of such inertial bodies, and discuss the properties of motion in observing it from this laboratory, which we would consider to be in the state of rest. If the properties of motion observed in some other laboratory would differ from the properties of motion observed in our laboratory, we would be warranted to say that the first laboratory was moving. Does the train move? After we establish that the motion in moving laboratory is governed by laws different from those that prevail in the inertial ones, the concept of motion will seem to have lost its relative character. We would then only have to imply the motion of relative inertia and refer to it as absolute. But will the laws prevailing in an inertial laboratory change in every case when the laboratory is moved? Let us board a train moving in a straight line at a uniform speed and observe the behavior of bodies inside the carriage, comparing it with that in a motionless train. Our daily experience tells us that in a train traveling rectilinearly at a constant speed of the motion of bodies is the same as in stationary train. A ball tossed into the air in a moving train will invariably drop back in your hands and will not describe a curve as shown on page 20. If we discount the jolting that is inevitable for technical reasons, everything that takes place in a moving train will also take place in a stationary one. It is a different thing when the train reduces or increases its speed. In the first case, we will experience a jolt forward, and in the second case, a jolt backward, quite distinct from the state of rest. If a train moving at constant speed changes its direction, we will also feel it at once. At a sharp right turn, we will be pressed against the left side of the carriage, and vice versa at a left turn. Summing up, we come to the conclusion that as long as a certain laboratory moves uniformly and rectilinearly relative to another laboratory that is in the state of rest, it is impossible to observe differences in the behavior of bodies in the latter laboratory. However, as soon as the motion of the moving laboratory changes, i.e. acceleration, deceleration, change of direction, The effect is instantly felt in the behavior of the bodies in it. The state of rest is lost forever. The amazing fact that a laboratory in uniform, rectilinear motion has no effect upon the behavior of the bodies in it compels us to revise our conception of the state of rest. It develops that the state of rest and the state of uniform and rectilinear motion do not differ. A laboratory which moves uniformly and rectilinearly relative to the one that is in a state of rest may itself be considered in a state of rest. This means that there is not one absolute state of rest, but a countless number of various states of rest. Hence, there is a countless number of laboratories in a state of rest, all of them moving uniformly and rectilinearly relative to each other at various speeds. Since the state of rest is relative and not absolute, we have to mention every time in relation to which of the countless laboratories moving uniformly and rectilinearly relative to each other we observe the given motion. Thus we have failed to make motion an absolute concept. In relation to what state of rest we observe the motion is in question, is a question that is forever open. We have thus come to the most important law of nature, usually called the principle of relative motion. It says that the motion of bodies within frames which move uniformly and rectilinearly relative to each other is governed by the same laws. The law of inertia, the principle of the relativity of motion, indicates that a body which is not influenced by an external force may be either in a state of rest or in a state of rectilinear and uniform motion, a condition which physicists call the law of inertia. However, in our daily life, the operation of this law is veiled and does not directly manifest itself. By the law of inertia, a body in a state of uniform and rectilinear motion should retain its motion forever even if no external forces act upon it. However, our observations show that if we do not apply force to a body, it is bound to become a standstill. The key to the riddle lies in the fact that all the bodies we see experience the effect of certain external forces, the forces of friction. The condition we need in order to observe the law of inertia, absence of external forces acting upon the body, is invaluable. But by improving the conditions of the experiment, i.e. by reducing the forces of friction, we may approach the ideal condition that required to observe the law of inertia, proving that this law is also valid for motions observed in our daily life. The discovery of the principle of relativity of motion is one of man's greatest discoveries. Physics would never have been able to develop without it. We owe this discovery to the genius of Galileo, who boldly opposed Aristotle's teaching, dominant at that time and strongly supported by the Catholic Church. According to Aristotle, motion was possible only if force was applied and would inevitably cease without it. Galileo proved the very contrary in a number of brilliant experiments. He showed that it was friction that brought moving bodies to a standstill, and that a body once put in motion would remain in motion forever if there were no friction. Velocity is relative, too. It follows from the principle of relativity of motion that the uniform and rectilinear motion of a body at a certain velocity is a meaningless concept, unless we say in relation to which inertial frame that certain velocity is measured. The same may be said about the concept of longitude if we do not say from what meridian it is to be measured. We thus find that velocity is also a relative concept. If we determine the velocity of one and the same body relative to different inertial frames, we will get different results. Yet each change of velocity, whether acceleration, deceleration, or change of direction, is absolute in meaning and does not depend on the position of the frame from which we observe it. Chapter 3. The Tragedy of Light. Light does not propagate instantaneously. We have convinced ourselves of the principle of the relativity of motion and of the existence of a countless number of inertial frames. In the latter, the laws governing the motion of bodies are similar. However, there exists a kind of motion which, at first glance, contradicts the principle we have established above. It is the propagation of light. Light does not propagate instantaneously, although indeed its velocity is tremendous. 300 300,000 kilometers per second to be precise. This colossal velocity is hard to conceive, since we usually deal with far inferior speeds. The speed of the latest Soviet space rocket, for example, is a mere 12 kilometers per second. Of all the bodies we deal with, the Earth has the greatest speed in its rotation around the Sun, but even so, the speed of the Earth is only 30 kilometers per second. So can the velocity of light be changed? The colossal velocity of light propagation is nothing very extraordinary in itself. Much more striking is the fact that this velocity is very constant. You can always accelerate or decelerate the motion of a body artificially, even of a bullet. All you need to do is to place a box of sand in its path. Having pierced the box, the bullet will lose its velocity. It is different with light. The velocity of a bullet depends largely on the design of the rifle it is fired from and the properties of gunpowder, while the speed of light is always the same no matter what its source. Let us place a plate of glass in the path of a beam of light. Since the velocity of light in glass is less than in vacuum, the beam will travel slower. However, having passed through the glass, the light ray gains the speed of 300,000 kilometers per second. Light propagation in vacuum, as distinct from all other kinds of motion, has this very important property. You cannot accelerate or decelerate it, no matter what changes the beam of light undergoes in matter. It propagates with the same velocity as soon as it emerges into a vacuum once more. Light and sound. In this respect, the propagation of light reminds us more of sound propagation than of the usual motion of bodies. Sound is the vibration of the media which it propagates. Therefore, the velocity of sound depends on the properties of the media and not on the properties of the sound-producing body. Sound velocity cannot be increased or decreased any more than light velocity, even by passing the sound through other bodies. If we place a metal barrier in its path, the sound will change its velocity inside the barrier. But as soon as it emerges again into its initial medium, it will regain its initial velocity. Let us place an electric bulb and bell under the glass hood of an air pump and proceed to pump out the air from under the hood. The sound of the bell will get weaker and weaker until it becomes altogether inaudible. The bulb, on the contrary, will radiate light as usual. This experiment proves that sound propagates in a material medium, while light propagates even in a vacuum. Therein lies the essential difference. The principle of relativity of motion seems to be shaken. The colossal but not infinite velocity of light in vacuum brings us into conflict with the principle of relativity of motion. Imagine a train hurtling along at the tremendous speed of 240,000 kilometers per second. We are riding in the head carriage, and an electric bulb is switched on in the end carriage. Let us see what results we would get if we measured the time necessary for the light to travel from one end of the train to the other. It would seem that this time would differ from the one we would obtain if the train were standing still. Indeed, relative to the train moving at 240,000 kilometers per second, the light should travel at a speed of only 300,000 to 240,000 kilometers. The colossal but not infinite velocity of light in vacuum brings us into conflict with the principle of relativity of motion. Imagine a train hurtling along at the tremendous speed of 240,000 kilometers per second. We are riding in the head of carriage, and an electric bulb is switched on in the end carriage. Let us see what results we would get if we measured the time necessary for the light to travel from one end of the train to the other. It would seem that this time would differ from the one we would obtain if the train were standing still. Indeed, relative to the train moving at 240,000 kilometers per second, the light should travel at the speed of only 300,000 minus 240,000, which is equal to 60,000 kilometers per second. It is as if the light has to catch up with the head carriage. If we place the bulb at the end of the train and measure the time necessary for the light to reach the tail carriage, it would seem that its velocity in the direction opposite to the movement of the train should be 240,000 plus 300,000, which is equal to 540,000 kilometers per second. The light and the tail carriage move towards each other. Thus it appears that in a moving train, light should propagate at different velocities in different directions, while in a train, which is at a standstill, the velocity of light is the same in both directions. It is quite different with a bullet. Whether fired in the direction of a train's movement or against it, the velocity of the bullet relative to the walls of a carriage will be one and the same, equal to the bullet's velocity in an unmoving train. The fact is that the velocity of a bullet depends on the speed of the rifle, while the velocity of light, as we have already said, does not change with the change in speed at which the bulb is traveling. Our argument seems to demonstrate that the propagation of light contrasts sharply with the principle of relativity of motion. A bullet flies at one and the same velocity relative to the walls of a moving and unmoving train, while in a train traveling at 240,000 kilometers per second, light apparently propagates 5 times as slow in one direction and 1.8 times as fast in the opposite direction as in an unmoving train. It would seem that a study of light propagation should enable us to establish the absolute speed of a train's motion. There is hope that we might establish the concept of an absolute state of rest by means of the phenomenon of the light propagation. The frame in which light propagates in all directions at the same constant velocity of 300,000 kilometers per second may be said to be in a state of absolute rest. In any other frame which moves uniformly and rectilinearly relative to ours, the velocity of light should be different in different directions. In that case, relativity of motion, relativity of velocity, and relativity of state of rest, which we have established above, do not exist. How is this to be conceived? At one time, physicists applied the analogy between the phenomenon of sound and light propagation to introduce a special medium, which they call ether, in which light propagated in the same way as sound propagated in air. They assumed that all bodies moving through ether do not propel the latter any more than a cage made of thin strips of wood floating in water does not propel the water. If our train is motionless relative to the ether, then light will propagate in all directions with the same velocity. The motion of the train relative to the ether will manifest itself at once in the fact that the velocity of light will be different for different directions. However, this introduction of ether, a medium whose vibration we observe in the form of light, gives rise to a number of pointed questions. To begin with, the hypothesis itself is obviously artificial. Indeed, we can study the properties of air not only by observing the propagation of sound in it, but also by various physical and chemical methods of research. Meanwhile, due to some mysterious reason, ether takes no part in most of the phenomena. Air density and pressure are easily measured by the crudest methods, yet all the attempts to learn something of the density and pressure of ether came to naught. The position is rather ridiculous. All phenomena of nature can, of course, be explained by introducing some special liquid possessing the desired properties. But the difference between the genuine theory of a phenomena and a single paraphrase of well-known facts with scientific terms lies precisely in the fact that a lot more follows from the theory than we get from the facts of which it is based. Take, for example, the conception of an atom. It was through chemistry that it was introduced into science, but our notion that atoms enabled us to explain and predict a great number of phenomena which have no relation to chemistry. The concept of ether may be justifiably linked into the explanation which a savage would have given the gramophone, to the effect that a special gramophone spirit was imprisoned in the mysterious box. Such explanations explain nothing. Physicists had an unfortunate experience of that kind prior to ether. There was a time when they explained the phenomenon of combustion by the properties of a special liquid they called phlogiston, and the phenomenon of heat by the properties of another liquid, heterode. These liquids, by the way, were no less elusive than ether. Difficult situation. But the main difficulty lies in the fact that violation of the principle of relativity of motion by light propagation should have inescapably led to the violation of the same principle by all other bodies. After all, any medium offers resistance to the motion of bodies. Therefore, the displacement of bodies in ether should also involve friction. The movement of a body should slow down, and finally it should come to a standstill, the state of rest. Meanwhile, the Earth is rotating around the Sun for many thousands of millions of years, according to geographical facts, and shows no trace of slowing down due to friction. Thus, by trying to explain the strange behavior of light in a moving train by the presence of ether, we have stumbled into a blind alley. The notion about ether does not eliminate the contradiction between violation of the principle of relativity by light and observance of it by all other motion. Experiment should decide. What is to be done with this contradiction? Before voicing our considerations on the score, let us turn to the following circumstance. The contradiction between light propagation and the relativity of motion has been derived by us exclusively through mental construction. It is true, we repeat, that this construction was very convincing, but if we confine ourselves to reasoning alone, we shall liken ourselves to an ancient philosopher who tried to produce the laws of nature out of his head. The inevitable danger arises that the world thus constructed may one day develop to be very much unlike the real one. Experiment is the supreme judge of all and every physical theory. Therefore, we shall not confine ourselves to arguments as to how light propagates in a moving train, and turn to experiment which will show how it propagates in reality to these conditions. Our experiment is facilitated by the fact that we ourselves live on a moving body. Rotating around the Sun, the Earth does not rectilinearly and cannot therefore be a permanent state of rest relative to any other frame. Even if we take a frame relative to which the Earth is motionless in January, it is certain to be in motion in July, since the direction of the Earth's rotation round the Sun changes. Therefore, studying light propagation on the Earth, we in fact study it within a frame that moves at a speed of 30 kilometers per second, something quite considerable in our conditions. The rotation of Earth round its axis of the order of nearly half a kilometer per second may be ignored. Are we justified, however, to liken our globe to the moving train which we discussed above and which led us into a blind alley? The train was moving uniformly and rectilinearly, while the Earth rotates orbicularly. Yes, we are justified to do so. The Earth may be justifiably considered to be moving uniformly and rectilinearly in that infinitesimal fraction of a second which it takes light to pass through the points of observation. The margin of error is so very insignificant that it cannot be detected. But since we have the likened train and Earth, it would be natural to expect that light on the Earth would behave just as strangely as it did in our train, that it would propagate in different directions at different velocities. Principles of relativity triumphs. An experiment of this kind was made in 1881 by Albert Michelson, one of the 19th century greatest experimenters who measured the velocity of light propagating in different directions with a high degree of accuracy. To detect the slight anticipated difference in velocity, Michelson used very precise and ingenious experimental equipment. The accuracy of his experiment was so high that he would have been able to detect far smaller differences in velocity than the anticipated ones. The Michelson experiment, later repeated under various conditions, led to quite unexpected results. In a moving frame, light propagated quite differently from what we had inferred. Michelson discovered that on the rotating Earth, light propagated in all directions at the same time constant velocity. In this respect, light propagation reminds us of the flight of a bullet. It is independent of the motion of the frame, and its velocity relative to the walls of the frame is the same in all directions. Michelson's experiment thus proved that, contrary to our inference, the phenomenon of light propagation, far from contradicting, fully agrees with the principle of relativity of motion. In other words, all our reasoning on page 25 was erroneous. out of the frying pan into the fire. We have cast off the uneasy contradiction between the laws of light propagation and the principle of relativity of motion. The contradiction was only a seeming one due to our erroneous reasoning. Why did we make our mistake? For nearly a quarter of a century, from 1881 to 1905, physicists ranked their brains over this problem. Yet all their explanation inevitably led to new contradictions between theory and practice. If the source of the sound and the observer travel in a cage made of thin rods, the observer will feel a strong wind. If we measure sound velocity relative to the cage, it will be less in the direction in which the cage moves than in the opposite direction. However, suppose we place the source of sound in a carriage in which all windows and doors are tightly shut and measure its velocity. We shall discover that since the air inside the carriage is not affected by the movement of the carriage, sound velocity in it will be the same in all directions. If we take light instead of sound, we could make the following assumptions to explain Michelson's experiment. The Earth does not leave the ether undisturbed, as does the cage of thin rods, when hurtling through space. On the contrary, we assume that it carries the ether along with it, that in movement it comprises a single whole with it. In that case, the outcome of Michelson's experiment is absolutely understandable. But this assumption conflicts with a great number of other experiments, such, for example, as propagation of light in water flowing through the tube. If our assumption about ether being carried along by the Earth were right, then by measuring the velocity of light in the direction of the flow, we would obtain a velocity equal to the velocity of light in motionless water, plus the velocity of the flow. But as a result of our measurement, we get a smaller velocity than we should if our assumptions were right. We have already mentioned the extremely strange phenomenon of bodies not experiencing any friction to speak of when passing through ether. But if they not only pass through ether but carry it along with them, the friction should be greater. Thus, all attempts to go round in the contradiction that arose after the unexpected outcome of Michelson's experiment failed. Let us sum up. Michelson's experiment reconfirms the principles of relativity of motion, not only for ordinary bodies, but also the light propagation, and hence for all natural phenomena. As we have already seen, the relativity of velocity stems directly from the principle of relativity of motion. Different frames moving relative to each other should have different speeds, but on the other hand, slight velocity of 300,000 kilometers per second is the same for all the frames. Therefore, it is absolute and not relative. Chapter 4. Time is relative. Is there really a contradiction? At first glance, it may seem that we are dealing with a purely logical contradiction. The consistency of the velocity of light propagating in all directions is ample proof of the principle of relativity. At the same time, the velocity itself is absolute. Let us recall, however, how the medieval man treated the fact that the earth was round. To him, the roundness of the earth was conflicted with the force of gravity, since he thought that all objects had to roll off the earth's surface. Yet we know perfectly well that there is no logical conflict at all. Simply the concepts of up and down are relative and not absolute. The same holds true for a propagation of light. It would have been futile to look for a logical contradiction between the principle of relativity of motion and the absoluteness of the velocity of light. The contradiction appears when we introduce other assumptions, much in the way people in the Middle Ages have done when they refuted that the earth was round by treating the concept of up and down as an absolute concept. Their absurd belief stemmed from insufficient experience. People traveled very little at the time and knew only small areas of the earth's surface. Evidently, something similar happened to us. Our insufficient experience made us believe something relative to be absolute. What? To spot our own mistake, we shall from now on accept nothing but suppositions established by experiments. Boarding a train. Picture a train 5,400,000 kilometers long, traveling rectilinearly and uniformly at a speed of 240,000 kilometers per second. Suppose a lamp is switched on at some given instant, somewhere in the middle of the train. And suppose the automatic doors in the front and rear carriages open the moment the light of the bulb reaches them. What will the people of on board of the train see, and what will the people standing on the platform see? In answering this question, we will, as agreed, abide solely by experimental data. People in the middle of the train will see the following. Since, according to Michelson's experiment, light travels relative to the train at one and the same velocity in all directions, 300,000 kilometers per second, it will reach the rear and the front carriages simultaneously, 9 seconds later. And both doors will open at the same time. Relative to the station platform, the light also travels at a speed of 300,000 kilometers per second, but the rear carriage moves to meet the light beam. Therefore, the beam of light will reach the rear carriage after 2,700,000 divided by 300,000 plus 240,000, which is equal to 5 seconds. The beam must catch up with the front carriage and therefore will reach it 45 seconds later. It will seem to the people on the platform that the doors open at different times. The rear door first and the front door 45 minus 5 equaling 40 seconds later. Thus, two absolutely identical functions, opening of the front and the rear doors of the train, will happen at the same time for people on board the train and with a 40-second interval for people on the platform. Therefore, common sense is disgraced. Is there any contradiction in this? Perhaps the fact that we have discovered is as absurd as saying that an alligator measures 2 meters from head to tail and 1 meter from tail to head. Let us try and see why the result we have attained seems absurd in spite of conforming with experiments. Hard as we may think, we shall never find any logical contradiction in the fact that two phenomena which happened simultaneously for people on the train were 40 seconds apart for people on the platform. Our conclusions are a hallowing contradiction to common sense. That is the only thing we can say to console ourselves. But remember how the common sense of the medieval man revolted against the fact that the earth rotated around the sun. Indeed, the medieval man's experience told him indisputably that the earth was standing still, and that the sun rotated around it. And was it not common sense that we have to thank for the ridiculous proof that the earth could not be round? The conflict of common sense, which, a real fact, was ridiculed in a well-known joke about a cowboy who explained it can't be upon seeing a giraffe in the zoo. The so-called common sense is no more than a summing up of concepts and habits formed in everyday life. It represents a certain level of apprehension reflecting the extent of our experience. The difficulty of perceiving and understanding that two events occurring simultaneously on the train are 40 seconds apart when seen from the platform is very much like the difficulty the cowboy had when he saw the giraffe. Like the cowboy had never seen the animal, so have we never traveled at speeds anywhere close to the fantastic speed of 240,000 kilometers per second. It is not surprising that when physicists encounter such fantastic speeds, they observe facts which considerably differ from the things we are accustomed to in our everyday life. The unexpected outcome of Michelson's experiment furnished physicists with new facts and forced them to re-examine, in defense of common sense, such, it would seem, obvious and commonplace concepts as simultaneously as two events. It would have been simpler, of course, to deny the new phenomena on the grounds of common sense, but if we did, we would linken ourselves to the cowboy who wouldn't believe his eyes when he saw a giraffe. Science does not hesitate to come into conflict with so-called common sense. What it fears most is inconsistency between existing concepts and new experimental data, and if ever that occurs, it smashes the existing conceptions and raises our knowledge to a higher level. We thought that two simultaneous functions are simultaneous within any frame. Our experiments proved, however, that we were wrong. It applied solely in the case when the frames were in a state of rest relative to each other. If, on the other hand, two frames were in motion relative to each other, the functions occurring simultaneously in one of them should be regarded as occurring at an interval in the other. The concept of simultaneity becomes relative. It has sense only if we specify the motion of the frame in which the functions are observed. Let us recall the example of the relativity of angular values on page 10. Let the angular distance between two stars observed from the Earth be 0, due to the two stars being aligned. In our everyday life, we shall never come into conflict with the assumption that this is an absolute truth. It is different if we go outside the solar system and observe the same two stars from some other point in space. We would find the angular distance quite distinct from 0. The fact that two stars, which are aligned when observed from Earth, may not be aligned when observed from other points in space, quite obvious to our contemporaries, would have appeared absurd to the medieval man who conceived the sky as a cupola sprinkled with stars. Let us assume that we were asked whether, apart from frames of all kinds, the two events really occurred simultaneously. Unfortunately, this question has no more sense than whether, apart from all points from which we conduct our observations, the two stars are generally aligned. The fact is that simultaneity depends not only on the two functions, but also on the frame from which we observe these functions, just as alignment of the two stars depend not only on their position, but also on the point from which they are observed. Until we dealt with these speeds that were insignificant compared with the velocity of light, the relativity of the concept of simultaneity was unknown to us. It was only when we examined motion at velocities comparable to that of light that we were compelled to re-examine our concepts of simultaneity. In the same way, people had to revise their conception of up and down when they began to travel over distances comparable with the dimensions of the Earth. Before that, the conception that the Earth was flat did not, of course, conflict with experience. True, we are not able to travel at velocities anywhere the speed of light to observe all the facts we have just discussed, which are paradoxical from the standpoint of our old concepts. But thanks to modern experimental techniques, we are able to reveal these facts conclusively in a number of physical phenomena. Time thus shares the fate of space. The words "at one and the same time" are just as meaningless as the words "in one and the same place." The interval between two functions, like distance between them in space, has to be supplemented by a reference to the frame in relation to which it's defined. The discovery that time is relative radically changed man's ideas about nature. It represents one of the greatest victories of human reason over backward centuries-old conceptions. It is comparable only to the revolutionary change occasioned in human notions by the discovery that the Earth is round. The discovery of relativity of time, made in 1905 by the greatest 20th century physicist Albert Einstein, placed him, then a 25-year-old man, among the giants of human thought. Copernicus, Newton, and others, the trailblazers in science. Lenin called Albert Einstein one of the greatest transformers of natural science. The theory of relativity of time and its corollarities are usually known as the special theory of relativity. It is not to be confused with the principle of relativity of motion. Velocity has its limits. Before the Second World War, the speed of aircraft was far below the speed of sound. Today, we have supersonic aircraft. Radio waves propagate at the velocity of light. Could we perhaps create superlight telegraphy to send signals at velocity greater than the velocity of light? No, that is an impossible thing to do. Indeed, we could transmit signals at infinite velocities. We would be able to establish simultaneity of any two events synonymously. We would say that these two events happen simultaneously if the infinitely fast signal about the first event arrived at the same instant as the signal about the second event. Thus, simultaneity of the two events would have acquired absolute character, independent of the motion of the laboratory to which this affirmation applies. But since the experiment disproves absolute nature of time, we conclude that signal transmission cannot be instantaneous. The velocity of transmission from one point in space to another cannot be infinite. In other words, cannot be greater than some ultimate value, called the speed limit. This speed limit concurs with the light velocity. Indeed, according to the principle of relativity of motion, the laws of nature will be the same for all the laboratories moving relatively to each other, rectilinearly and with the same uniform velocity. The affirmation that no velocity can be greater than the given limit is also the law of nature, and therefore, the value of the speed limit should be exactly similar in different laboratories. The light velocity, as we know, possesses the same qualities. Thus, the speed of light is not merely the speed of propagation of natural phenomenon. It plays the important part of being the top velocity. The discovery of the existence in the universe of the top velocity is one of the greatest triumphs of human genius and the experimental capacity of mankind. In the 19th century, physicists were unable to perceive that a top speed existed and that its existence could be proved. Moreover, if they would have stumbled upon it by chance in their experiments, they would not have been sure that it was a law of nature or not merely the effect of the limited experimental capacity. The principle of relativity reveals that the existence of a top velocity lies in the very nature of things. To assume that technological development will enable us to attain velocities greater than the velocity of light is just as ridiculous as to suggest that the absence of points on the Earth's surface more than 20,000 kilometers apart is not a geographical law, but the upshot of our limited knowledge. And to hope that someday, when geography makes further advances, we shall be able to find points of the Earth that are still farther apart. Light velocity plays such an exceptional part in the nature exactly because it is the top velocity for the propagation of anything. Light either outstrips all other phenomena or, at the outside, arrives simultaneously with them. If the sun should split in two and form two stars, the motion of the Earth would naturally suffer a change as well. The 19th century physicist who did not know that a top velocity existed in nature would certainly assume that the Earth changed its motion instantly after the sun split in two. Yet, it would have taken light all of 8 minutes to cover the distance from the split sun to the Earth. The change in the Earth's rotary motion would begin 8 minutes after the sun split up. Until that moment, the Earth would continue to move as if the sun had not split. Anything that may occur with or on the sun will not affect the Earth or its motion until 8 minutes later. The top velocity of signal propagation naturally does not deprive us of the possibility of establishing simultaneity of two functions. All we have to do is note that the time lag of the signal, that it is the usual practice. This method of establishing simultaneity of action is quite compatible with the relativity of this concept. Indeed, to subtract the difference in time, we must divide the distance between two spots where the functions occurred by the velocity of the light signal. On the other hand, when we earlier discussed the letters sent from the Moscow Vladivostok Express, we saw that the location of a spot in space is also quite relative. Earlier and later. Let us assume that in our train with the lamp, which we call the Einstein train, the automatic device has failed and people in the train notice that the front door opened 15 seconds earlier than the rear one. On the platform, reversely, the people will notice that the rear door flew open 25 seconds later. A function that occurred earlier in one time frame occurred later in the case of another. It may occur to us that this relativity of the concepts of earlier and later should, when all is said and done, have its limits. It is not likely, after all, from the point of view of any frame, that a baby was born before its mother. Suppose a spot is formed from the sun. 8 minutes later, it is spotted by an astronomer observing the sun through the telescope. Anything the astronomer does after that will be absolutely later than the appearance of the spot, later from the standpoint of any frame from which the sun and the astronomer are observed. On the contrary, everything that happens to the astronomer earlier than 8 minutes before the appearance of the spot, the light signal, of this event reaching the sun before the appearance of the spot happens absolutely earlier. If, for example, the astronomer put on his glasses at some instant between the two borders, the time relation between the appearance of spot and putting on the glasses will no longer be absolute. We may now relative to the astronomer and the sunspot in a way as to observe the astronomer putting on his glasses earlier, later, or at one and the same time with the appearance of the spot, depending on the speed and direction of our movement. The principle of relativity thus demonstrates that three types of time relations exist between events: absolutely earlier, absolutely later, and neither earlier nor later, or to be more accurate, earlier or later relations, depending on the frame from which the events are observed. Chapter 5. Capricious Clocks and Rulers. We board the train again. We are riding in the Einstein train along an endless railway. The distance between two stations is 864 million kilometers. It will take this train traveling at 240,000 kilometers per second 1 hour to recover this distance. There are clocks at both stations. A traveler boarding the train at the first station sets his watch by the station clock. On arriving at the second station, he is surprised to find that his watch is slow. At the repair shop, he was told that his watch was in good order. What is the matter? To make it out, let us assume that the traveler sends a beam of light to the ceiling from a torch placed on the floor of the carriage. A mirror on the ceiling reflects them back to the torchlight. The beam path as seen by the traveler is shown in the upper section of the figure of this page. It looks quite different to the observer on the platform. During the time it takes the beam to travel from the torch to the mirror itself will shift to the motion of the train. During the time it takes the beam to travel back to the torch, to the latter will shift by the same distance. We notice that to the observers on the platform, on the beam clearly traveled a greater distance than those on the train. On the other hand, we know that the velocity of light is an absolute velocity, and that it is the same for those riding on the train and those who observe it from the platform. We conclude, therefore, that a greater interval elapsed at the station between the departure and return of the beam than on the train. The relation is easy to calculate. Suppose the observer on the platform established that 10 seconds elapsed between the departure and return of the beam of the light. During these 10 seconds, the beam traveled 300,000 times 10, which is equal to 3 million kilometers. It follows that sides AB and BC of the isosceles triangle ABC are 1,500,000 kilometers each. AC is evidently equal to the distance which the train travels in 10 seconds. 240,000 times 10, which is 2,400,000 kilometers. Now it is easy to find the height of the carriage, which is equal to BD, the height of the triangle ABC. Let us recall that in an equilateral triangle, the square of the hypotenuse AB is equal to the sum of squares of the legs AD and BD. The equation of AB squared equal to AD plus BD squared helps us find that the height of the carriage BD is equal to the square root of AB squared minus AD squared, which is equal to the square root of 1,500,000 squared minus 1,200,000 squared, which is equal to 900,000 kilometers. Quite a height that, although it is not too surprising, considering the astronomical dimensions of the Einstein train. From the point of view of the passenger, the path traveled by the beam from the floor to the ceiling and back again is obviously double the height. That is 2 times 900,000, which is equal to 1,800,000 kilometers. It will take 1,800,000 kilometers divided by 300,000, which is equal to 6 seconds for the beam to travel this distance. Clock paradox. While 10 seconds elapsed at the railway station, only 6 seconds passed on the train. This means that if the train arrived 1 hour after its departure according to the station clock, it traveled only 60 times 6 divided by 10, which is equal to 36 minutes by the passenger's watch. In other words, each hour his watch will be 24 minutes behind the station clock. It is easily seen that the greater the speed of the train, the greater the time-lag difference. Indeed, the closer the speed of the train approaches that of the light, the closer the leg AD, indicating the path of the train, approaches the hypotenuse AB, indicating the path traveled in the same time by the beam. The relation of the leg ED to the hypotenuse decreases correspondingly, yet it is this relation that represents the time relation of the train of the platform. By raising the speed of the train to approach that light, which we can reduce the time in the train to that an infinitesimal figure per hour of station time, at a speed equal to 0.9999 of that light, for example, only 1 minute will elapse on the train in 1 hour of station time. Consequently, all traveling clocks and watches lag behind timepieces in a state of rest. Does this contradict the principle of relativity from which we proceeded in our argument? Would it mean that the clock, which is faster than all other clocks, is in a state of absolute rest? No, this is not the case because the comparison between the watch in the train and the station clock was made under absolutely unequal conditions. Actually, there were 3 clocks and not 2. The traveler had checked his time again 2 different clocks at 2 different stations, and reversely, if there were clocks in the front and the rear carriage of the train, the observer comparing the station clock against those 2 on the train as it flashed by would discover that the station clock was always behind. Given that the train travels uniformly and rectilinearly in relation to the station, we are justified to consider it to be stationary and the station to be moving. The laws of nature operating in them should be the same. Each and every observer who is motionless in relation to this timepiece will notice that it is other clocks moving relatively to him that are fast, and that the clocks are at all the faster as the rate of their motion rises. This may be compared to 2 observers standing beside different telegraph poles, each claiming that the pole he is looking at is seen from a greater angle than the others. Time machine. Now, let us assume that the Einstein train travels along a circular railway and not a trunk line. It will then return after a certain time to its point of departure. As we have already established, the passenger will discover that his watch is slow, and the faster the train goes, the slower his watch will be. By increasing the speed of the train, we may reach a point where only 1 day passes for the passenger, while the number of years elapse for the station master. So many years may elapse, as a matter of fact, that on returning home to the station of departure after a day's journey by his own watch, our passenger will learn that all of his relatives and friends are long since dead. During this journey by the circular railway, the time of only 2 timepieces is compared, in the train and at the station of departure. Is there anything in this that contradicts the principle of relativity? May we consider that the passenger is in a state of rest and that the station of departure is moving around the circle at the speed of Einstein's train? We would then come to the conclusion that only a day passes for the people at the station, whereas many years elapse for the passengers on the train. This would be an incorrect inference. Here is why. We have established above that a body may be considered stationary only if it does not experience the effects of an outside force. There is, it is true, more than just one state of rest. There is a countless number of them, and 2 stationary bodies may, as we know, move rectilinearly and uniformly relative to each other. But the watch in the Einstein train speeding round the circular railway experiences the effects of centrifugal force, and we cannot, therefore, consider it to be in a state of rest. The difference between the readings of the station clock and the watch in the train is absolute. If 2 people whose watches show the same time part and then meet again, the watch of those who was in a state of rest or moved uniformly and rectilinearly would be fast, for it would not have experienced the effects of any force. A journey on the circular railway at a speed close to that of light enables us to visualize Wells' time machine, if only to a limited extent. For on returning finally to our station of departure, we would step out of the carriage far into the future. We can go in the train to the future, but we cannot return to our past. Therein lies the big difference between the Einstein train and Wells' time machine. It is no use hoping that we shall ever be able to travel into the past, no matter how far science progresses. If the reverse were true, we should be compelled to admit that truly absurd situations are possible in principle. Just imagining the setting of the past and landing in the utterly absurd predicament of a person whose parents have not yet been born. Travel into the future involves no more than seeming contradictions. Traveling to a star. There are stars in the sky which are so far away from us that a beam of light takes 40 years to reach them. Since we already know that it is impossible to travel faster than the speed of light, we can well draw the conclusion that the star cannot be reached in less than 40 years. However, this inference is erroneous because we did not consider the time contraction involved in motion. Suppose we fly to the star in an Einstein rocket at a speed of 240,000 kilometers per second. For people on the Earth, we will reach the star in 300,000 times 40 divided by 240,000, which is equal to 50 years. But for us on board, the rocket time flying at the mentioned speed will shrink at a ratio of 10 to 6. Hence, we will reach the star in 6 to the 10th times 50, which is equal to 30 years, and not in 50. We can reduce this flying time indefinitely by raising the speed of our Einstein rocket until it approaches the speed of light. Theoretically, traveling at a sufficiently high speed, we can reach the star and return to Earth within a minute, but on the Earth 80 years will have passed just the same. To all appearances, we thus possess a way of prolonging human life, though only from the point of view of other people, since man ages according to his own time. To our regret, however, this prospect is illusory if we take a closer look at it. To begin with, the human body is not adapted to a state of prolonged acceleration exceeding the Earth's force of gravity to any visible extent. It will require a considerable time to accelerate to speeds close to that of light. Calculations show that in 6 months of traveling at an acceleration equal to that of Earth, our gain will amount to a mere 6 weeks. If we prolong our trip, the gain in time will increase sharply. 12 months in a flying rocket will yield an additional gain of 18 months. 2 years of traveling will give a gain of 28 years. And if we spend 3 years in interplanetary travel, we will gain more than 360 years. Very comforting figures, don't you think? The matter is very less cheerful when we come to the expenditure of energy. A rocket weighing a mere 1 ton and flying with a speed of 260,000 kilometers per second, the speed required to double at the time, for a year in the rocket to be equal to 2 on Earth, consumes 250 trillion kilometer watts hours, an amount which takes the world several months to produce. However, that is only what the rocket consumes in flight. We still have to figure out how much power it takes to accelerate our vehicle to the speed of 260,000 kilometers per second. And yet more power will be needed at the end of the flight to decelerate the spaceship for a safe landing. How much power would that require? It would still be 200 times as much as the amount we cited as above, even if we had fuel enough to produce a jet escaping the engine at the highest speed possible, the speed of light. In other words, we would have to consume an amount of power that the world produces in several dozen years. Actually, the jet escape velocity is scores of thousands of times less than the speed of light, making the power expenditure required for our imagined flight fabulously great. Length contraction. Time, as we have seen, is not really an absolute concept. It is relative and requires precise indication of the first frames from which observation is conducted. Now let us return to space. We found that even before discussed Michelson's experiments, that space is relative. Yet despite the relativity of space, we attributed an absolute character to the dimensions of bodies. In other words, we considered them to be properties of the body which did not depend on the frame from which we conducted our observations. However, the theory of relativity makes us abandon this conviction as well. Like our notion about time being absolute, it is a prejudice that we have developed because we always deal with the speeds indefinitely smaller than the speed of light. Let us imagine that the Einstein train rushes past a station platform 2,400,000 kilometers long. The train travels from our end of the platform to the other in 2,400,000 over 240,000, which is equal to 10 seconds by the station clock. But by the passenger's watch, it will take the train only 6 seconds. The passengers will be fully justified to conclude that the platform is not 2,400,000 kilometers, but 240,000 times 6, which is equal to 1.44 million kilometers long. The length of the platform, as we see, is greater from the point of view of the frame, which is stationary relative to it, than from the point of view of the frame relative to which the platform is moving. All moving bodies contract in the direction of their movement. However, this contradiction does not prove at all that motion is absolute. The body acquires its true dimension as soon as we view it from the frame that is stationary relative to the body. Likewise, the passengers will find that the platform has contracted, while the people on the platform will think that it is the Einstein train that has become shorter, ratio of 6 to 10. Nor will this be an optical illusion. All instruments used in measuring the length of a body will show it too. The connection with this discovery we must now correct the inferences in which we made on page 31 about the time it takes for the doors to open in Einstein's train. When we were calculating the time when the doors open from the point of view of an observer of the platform, we assumed that the length of a moving train was the same as of a stationary one. Yet the train was shorter for people on the platform. Accordingly, the interval between the time of the doors opened from the point of view of the station clock will actually amount to only 6/10 times 40, which is equal to 24 seconds, and not 24 seconds. Naturally, this correction is not essential for the conclusions we have made earlier. The figures on page 57 shows the Einstein train and the station platform as seen by observers at the station and on the train. We see that in the figure of the right, the platform is longer than the train, and in one of the left, the train is longer than the platform. Which one of these figures corresponds to reality? The question is senseless, just as the question about coward and the cow on page 9. These two phenomena are snapshots of one and the same reality taken from different points of view. Capricious speeds. What is the speed of a passenger relative to the railway bed if he walks at 5 kilometers per hour towards the head of a train traveling at 50 kilometers per hour? It will evidently be 50 plus 50, which is 55 kilometers per hour. Our answer is based on the velocity addition formula, and we have no doubt whatsoever that this is correct. Indeed, the train will have traveled 50 kilometers and the man on the train an additional 5 kilometers an hour. Hence the total of 55 kilometers. It is obvious that the existence of a top speed makes the law of adding velocities inapplicable universally to small and large speeds. If the passenger were traveling in the Einstein train at a speed of, say, 100,000 kilometers per second, his speed relative to the railway bed would have to be 240,000 plus 100,000, which is equal to 340,000 kilometers per second. But there is no such speed because it exceeds the speed of light. Consequently, the law of adding velocities, which we use every day, is not entirely accurate. It applies only to speeds far lower than that of light. The reader, who is now accustomed to all sorts of paradoxes in connection with the relativistic theory, will easily understand why the seemingly obvious reasoning, whereby we have just deduced the velocity addition law, is inadequate. We've added the distance traveled by the train in 1 hour and that of the passenger of the train. However, the theory of relativity showed us that these distances cannot be added. This would be just as absurd as multiplying AB by BC to find the area of the section of a road shown in the figure of this page, forgetting that the latter is distorted in the figure due to the perspective. Besides, to obtain the passenger speed relative to the station, we must find the distance traveled by him in 1 hour by the station clock, and to obtain his speed on the train, we must use the train watch, which, as we already know, is not the same by far. This brings us to the conclusion that velocities, of which at least one is comparable to that of light, are added in quite different manner from what we are accustomed to. We can observe this paradoxical addition of velocities experimentally when, for example, watching the propagation of light in flowing water. We've discussed this earlier. The fact that the velocity of light propagation in flowing water is not equal to the sum of the velocity of light in still water and the velocity of flowing water, but smaller than their sum, is to be directly attributed to the theory of relativity. Velocities are added in a very peculiar manner, if not of them is exactly 300,000 kilometers per second. This velocity, as we know, possesses the property of remaining unchanged, regardless of the motion of the frames of which we observe it. In other words, if we add any velocity to 300,000 kilometers per second, we will yet again get the same 300,000 kilometers per second. A simple parallel can be drawn in reference to the inapplicability of the usual rule of velocity addition. As you know, in a flat triangle, see left figure on the left, page 56, the sum of angles A, B, and C is equal to 2 right angles. Now let us imagine a triangle drawn on the Earth's surface. The sum of the angles of this triangle will be greater than 2 right angles due to the roundness of the Earth. The difference becomes visible only when the size of the triangle is comparable to that of Earth. We can use the ordinary rule of velocity addition when dealing with the insignificant speeds, just as it is possible to apply the rules of plane geometry to measuring small areas of the Earth's surface. Chapter 6. Mass. Suppose we want to make some inertial body move at a definite speed. We shall have to apply a certain force to it. The body will come into motion and may be accelerated in time to any desired velocity if there is no external force to prevent it, such as friction. We will find that different time intervals are required to accelerate different bodies to the desired velocity with the help of a given force. To get away from the force of friction, let us imagine in space 2 spheres identical in size, one made of lead and the other of wood. Let us apply the same force to each of them until they are accelerated to the speed of, say, 10 kilometers per hour. Evidently, we shall have to apply this force to the lead sphere for a greater length of time than to the wooden sphere. We say that the lead sphere has a greater mass than the wooden one. Under the actions of a constant force, velocity grows proportionately to the time. Therefore, the mass is the relation of time required to accelerate an inertial body to that velocity. The mass is proportional to this relationship, the coefficient being dependent on the accelerating force. Increasing mass. Mass is a most important property of any body. We are used to the mass of body always being constant. It does not depend on velocity. This follows from our initial contention that under the continuous application of a constant force, the velocity grows in direct proportion to the time of its application. This contention is based on the simple rule of adding velocities. However, we have just proved that this rule cannot be applied in all cases. What do we do to obtain the speed after a force has been applied for, say, 2 seconds? We conform to the ordinary rule of addition and add the speed of the body at the end of the first second to the speed it acquired during the second second. We can do so until the velocities approach the speed of light. In that case, the old rule becomes inadequate. Adding velocities with due account of the theory of relativity, we will get results somewhat smaller than we would if we were to use the old rule of addition, quite useless in this case. This means that a high velocity will no longer increase proportionately to the time a force is applied, but somewhat slower. This is only natural because there is a top velocity. Given a constant force, the velocity of a body increases slower and slower as it approaches that of light, so that the top velocity is never exceeded. Mass could be considered independent of the velocity of a body as long as we say that body velocity increased proportionately to the time a force is applied to it. But as soon as velocity approaches that of light, the proportion between time and velocity disappears, and mass becomes dependent on velocity. Since the time of acceleration grows indefinitely, and velocity cannot be greater than the top limit, we observe that mass grows with velocity, and it becomes infinite when body velocity reaches that of light. Calculations show that the mass of a moving body increases as much as its length diminishes. Thus, the mass of the Einstein train moving at 240,000 kilometers per second is 10/6 times greater than the mass of the same train at rest. It is quite natural that in dealing with conventional velocities, significant compared to the velocity of light, We may disregard the change in mass just as we disregard the connection between the dimension and speed of a body, or the connection between the time interval between two events and the velocities with which the observers of these events travel. We can check the relation between mass and velocity, which stems from the theory of relativity, by experiment of watching the motion of fast electrons. In modern experimental devices, an electron moving at a velocity close to that of light is quite commonplace. Electrons are accelerated in special installations called accelerators to speed only 30 kilometers per second slower than the speed of light. It turns out that modern physics is quite capable of comparing the mass of electrons moving at a great speed with the mass of stationary electrons. Experiments have fully confirmed that mass is related to velocity, a corollary of the principle of relativity. What is the price of a gram of light? The increment of body mass is closely connected with the work applied to it. It is proportional to the force required to set the body in motion. There is no need to expend work in merely setting the body moving. All force applied to the body, any increment of body energy, increases its mass. This is exactly why a body has greater mass when heated, why a spring has greater mass when it is compressed. True, the coefficient of proportionality between the change of mass and change of energy is insignificant. To add a gram of mass of a body, we should have to apply 25 million kilowatt hours of energy. That is why the change in body weight in ordinary conditions is very insignificant and evades the most accurate measurements. Thus, if we heat a ton of water from zero up to boiling point, its mass will increase approximately by 5 millionths of a gram. If we burn a ton of coal in a closed furnace, the products of combustion will have a mass 1/3000th of a gram less than the original coal and oxygen. This missing mass is carried away by the heat generated in the process of burning. However, in modern physics, we also observe phenomena where the change of mass plays quite a prominent role. Take the phenomena that occur when atom nuclei collide and new nuclei appear as a result. When, for example, an atom of lithium collides with an atom of hydrogen, producing two atoms of helium, the mass changes by 1 to the 400th of its original value. We have already said that to increase the mass of a body by 1 gram, we must apply as much as 25 million kilowatt hours of power. Hence, to convert a gram of lithium and hydrogen into helium, 400 times less energy is required. Now let us try and answer the following question. What substance exists in nature is the most expensive if we go by weight? Radium is considered to be the most expensive. Until recently, 1 gram of it was said to be worth about 250,000 rubles. But let us see the cost of light. In an electric bulb, we get a return of just 1/20th of spent energy in the form of light. Therefore, a gram of light is equivalent to 20 times as much work as 25 million kilowatt hours. In essence, 500 million kilowatt hours. That will add up to as much as 5 million rubles if we assume that a kilowatt hour costs only 1 kopek. It follows that a gram of light costs 20 times as much as a gram of radium. To sum up, precise and very convincing experiments make us admit that the theory of relativity, which reveals most amazing features in the world about us, is correct. These features evade us at the first cursory glance. We have seen the far-reaching and radical changes introduced by the theory of relativity to the basic concepts that man has worked out through the centuries of everyday experience. Does it mean that the physics developed long before the appearance of the theory of relativity is to be thrown overboard like an old and useless shoe? If this were so, there would be no call to engage in scientific research. Some new theory would be sure to appear and crush the old one. Imagine a passenger riding in an ordinary express, adjusting his watch because according to the theory of relativity, it would be behind the station clock. Everyone would make a laughingstock of him. The effect of, say, a jolt on a highly precise watch is far greater, not to mention the fact that the difference in question amounts to a microscopic fraction of a second. The chemical engineer who doubts whether water retains its mass when heated is clearly out of his mind. And yet, reversely, the physicist dealing with colliding atoms, nuclei, without accounting for the change in their atomic weight would be asked to leave the laboratory for being ignorant. Designers develop and will continue to develop their engines in accordance with the old laws of physics, because if they were to introduce corrections based on the theory of relativity, these corrections would have less effect upon their machines than a microbe settling on a flywheel. Physicists experimenting with fast electrons must bear in mind the change in their mass in relation to speed. The theory of relativity, far from refuting previous concepts and notions, extends them and defines the boundaries within which these old concepts may be applied without incurring the danger of error. The laws of nature discovered by physicists prior to the birth of the theory of relativity are not recited at all. It is only that their use is now more clearly defined. The correlation between the physics based on the theory of relativity, known as relativistic, and the physics of the old school, known as classical, is approximately the same as between higher geodesy, which takes into account the roundness of the Earth, and basic geodesy, which ignores it. Higher geodesy proceeds from the relativity of the vertical, and relativistic physics takes note of the relativity of the body dimensions and the time interval between any two events, while classical physicists know nothing of the concept of relativity. Just as higher geodesy developed from basic geodesy, so did relativistic physics develop and extend classical physics. We can shift from the formulas of spherical geometry, the geometry of the surface of spheres, to the formulas of plane geometry if we assume the radius of the Earth to be infinitely long. The Earth will then no longer be a sphere but an infinite plane. The vertical will be absolute, and the sum of the angles in a triangle will be exactly equal to the two right angles. A similar shift may be made in relativistic physics if we assume that the velocity of light is infinitely large, that is, propagation of light is instantaneous. Indeed, if light propagates instantaneously, the concept of simultaneousness, as we have seen, becomes absolute. The time intervals between events and body dimensions becomes absolute as well, regardless of the frames or laboratories from which they are observed. Consequently, we may retain all classical concepts if we consider the velocity of light to be infinite. However, the attempt to combine the ultimate velocity of light with the old concept of space and time puts us in the absurd position of a person who knows that the Earth is round but insists that the vertical of his native town is an absolute vertical and does not step outside town limits for fear of tumbling into space.